But again, I'm really sorry that you might get very well kicked out. So be careful about this. The class is going to be recorded and on YouTube, and it's going to be playing on the screen right outside. Like you can just sit right outside and walk inside if you have a question. But I'm somehow not able to get my slides to show. AV. I can't get the, excuse me? Hey, sorry, I need to access this.
Sorry.
Why am I not able to get this to, usually this just works.
So you have to connect the HDMI?
I did not know that. Okay, that's what. I connected the wrong connector. Okay.
And you're just gonna mirror?
Yeah. Hello.
External mirror.
Start mirroring. Slideshow. Let's see, does this work?
And then you want your audio to be. You want it to.
Got it.
Now you go back into your slides. And then the volume control for your laptop is this black one.
Okay, thank you.
Slideshow.
Okay. Okay, great. Welcome to the very first lecture for 182-282A. As you can see, there are more of you than there are seats in the class. We are very, very happy to have you here, and we will be talking about enrollment in just a minute. Before I officially start lecture, I want to just announce that the fire marshal requires us to not have anyone sitting in a non-seat, so please do your best to keep the aisles clear. The lecture will be live streaming on the screen that is right outside this room, so you can go, easily watch it out there, and if you want, walk in if you have a question, as an option to you. Okay, with that out of the way, let us start. Today's agenda is pretty simple. We're going to start with some introductions, then we're going to talk about some administrative details that I'm sure many of you have questions about, and then we will start doing some deep learning. So, this class has two professors. My name is Girija Ranade. I've been teaching in this department for a while. Before I started on the faculty at Berkeley, I was a researcher at Microsoft Research up in Seattle. So if you ever want to go hiking, it's an amazing place to be. Before that, I got my PhD actually right here at Berkeley, and I was an undergraduate at MIT. I was lucky enough to take the introductory AI class there with Patrick Winston, who is, one of my research and teaching idols and has been a foundational figure in the field of AI for since its beginning. One of the great things that he used to do when he started lecture was he would always start lecture by playing rock and roll. And the beautiful thing that he told me that has stuck with me to this day is that all great ideas are simple. Good ideas are complicated. So what we are going to try and do in this class is going to try and take these, ideas that have complications, that have lots and lots of nuances, and try to present to you the simplest, cleanest, most aesthetically pleasing version that you can use to solidify your understanding that will then help you actually, get further in the field. So this is going to be a class that is going to have a mix of a lot of mathematics as well as a lot of programming. And to be able to see the simplicity and the beauty in many of these ideas, we're going to be relying on the fact that you have taken and have a good handle and understanding of elegant and powerful mathematical tools. Because things are simple when they're looked at in the right language and with the right perspective, right? We know this from the SVD. When you project into the right coordinates, things become simple and clear. So that's the aesthetic that we will be taking. And so we'll talk more about the prerequisites, but that's something that I would like you to keep in mind.
Hi, I'm Professor Sahai. I've also been teaching here, but for longer. But I've taught this class a few times in the past. So we've learned a lot, and hopefully you will be the beneficiaries of that learning.
Yeah, it's my first time teaching the class. I should announce that. We will have office hours right after class in 400 Corey, so we can kind of all walk over together to that room when you have extra questions. In terms of resources, there is a website for the class, eeks182.org. All of our policies are documented on that website, so please feel free to look at them. There will be an ed for the class, which will be the primary mode of communication with you. All posts that are put onto ed are required reading. And please use ed as your forum for asking any kinds of questions, including administrative questions that you might need. Both the faculty members will be checking ed and will be responding to ed. It's the fastest way to get a response to your question. Finally, we will not really be using this textbook per se, but if you want a textbook, this is the textbook that we recommend. It's a very recent textbook by Simon Prince. There are many, many things that are very elegantly done in this textbook, so I recommend you look at it. There's also many things that we will be doing that are not addressed in this textbook. We're going to try to bring to you some of the most recent advances in the field and digest papers and share them with you. So there will be things that are covered in the class that are not in this textbook. So it's not that it's not a one-to-one mapping, but this is a good reference. Okay, now about the elephant in the room, enrollment. So the class might expand, but we do not know, and we do not have control over it as instructors. We've been asking the department to expand the class since April. But this is not in our control. If you would like to make your voices heard, the department would be the place to make your concerns heard. We have a possible expansion approved, so we are doing our best to make those accommodations, but we yet cannot guarantee that we will be able to do this because we were only given this information a week ago. So we're trying our very, very best. Because of this, we are going to prioritize having people in the class who want to be engaged and are committed to doing the work. This means that we will have a homework 0 that will be due next week, and those students who do not submit homework 0 will be automatically dropped from the class so that other students can be let in. If you are on the wait list for this class and you would like to get in the class, please make sure that you do the homework as though you are enrolled in the class. Keep up with the material. Only those students on the wait list who have completed and submitted homework 0 will be let into the class, okay? We simply have no other choices given the extreme restriction on the number of seats that came to us from the department. Again, I emphasize this was not our choice. We tried really hard. Is Sultan here?
Sultan?
Sultan, are you here?
No.
Okay, well, maybe wait just a minute. Mm-hmm. Okay, so there will be weekly discussion sections that will be staffed. We will have, at this moment, only 1 GSI for the course and 2 UCS ones. So we will introduce them in just a minute. These sections are going to be Wednesdays 3 to 4 and 4 to 5. These sections are required. this material will help you in understanding the material. Discussion sections will start on Wednesday, September 3rd. You can choose any one section to attend. Both sections will cover the same material. Discussions will be crowded for the first few weeks, so bear with us. We will be posting discussion sheets, so you will be able to get access to the material. In terms of getting help, there will be instructor office hours right after the class. There will also be GSI office hours at a time that is yet to be determined. We will have discussion sections. We will have the Ed Forum. And the most important resource that you have in this class is each other. What you have to be able to do is be able to talk to each other, form study groups, have accountability mechanisms, and be able to work with each other. I want to talk about this one more minute, but I know you have a commitment to get to, right?
Yeah.
So why don't we do introductions for the two staff members that are here? Do you want to start? Why don't you come up here and use the mic? Okay, yeah.
Hi, everyone. I'm Patrick. I am a fourth-year studying EECS and Applied Math. This is my first time on staff, and I'm very excited to work with all you all this semester.
Hi, my name's Alex. I'm a third year. I'm studying EECS and Math, and like Patrick said, I'm really excited to work with all you guys and to help you guys learn machine learning, help you guys learn deep learning. Sorry, on class. Yeah, this is my favorite class, and also it's my first time on course stuff. So, yeah, I'm excited to see you guys.
Okay. We have another GSI, Sultan Daniels, who is not here yet, but will be an excellent GSI. I have absolutely no doubt about that. Okay, so back to how to get help. Basically, we are your resources. As you can see, there are more of you than there are of us. It is actually a particularly low-staffed semester, so we will do our best to try and help you. But realize that there's just a limit to what we can do with the volume in this class. So that what that means is that it is really, really important that you form study groups and work together with each other to hold each other accountable to doing things like coming to lecture. I know for those of you sitting in the not in seats, it's not a particularly great environment to start. You're like, well, maybe I want to sit in a chair. Maybe I don't want to really be here and lecture. Odds are that in a week or two, this is going to thin out, and there's going to be plenty of room in the class. So please try to show up. Make accountability buddies so that you have reason to show up to class. And even if the first lecture, like, you know, you don't get a seat, odds are you're going to get a seat in the coming days. So, you know, really make sure that you make it a priority to be here. This is a great way to get to know people. What I also recommend is making a group of 3 to 5 to 8 people, however many you want, and setting a time where you will work together on your homework. Put it on your schedules like a class and come at that time and meet and do the homework. This is going to be a very fast-moving class, just given the sheer volume of material that we have to cover. And if you are not kept up with the homework, it's going to be really hard to digest all the material. So use each other to do that. Wonderful. Sultan is here. Do you want to introduce yourself?
Yes. Hi, my name is Sultan. I'm a third-year PhD student working on research on deep learning, and I took this class last semester and had a great time, and I'm really excited to teach everyone.
Great. Okay. If you have private questions that are not suitable for Ed, you may email the faculty to be able to get a response. But know that Ed is probably the fastest way to get a response. Our emails are often flooded, but we make time to go to Ed to respond to questions. And if you make a private post there, we will do our best to respond very, very quickly. I will apologize in advance that we might write to you very, very short 3-word emails. That is not because we are trying to be rude. It is simply because we are trying to reply to all of the questions we have received. I would rather reply to everyone shortly than write a long paragraph to one person and not reply to the other 10, okay? So we are really not trying to be curt or rude when we write short emails to you. Okay, great. Accommodations. We're happy to work with the DSP office to make sure that all of you have the appropriate accommodations for you to succeed in this class. Please reach out to us as needed. Homework extensions in this class will essentially be automatic if you need them. Project extensions, which we will talk about, we will not be able to offer simply because the project will be due at the end of the semester, and then we have to submit final grades. So there'll be a long period of time for you to do the project, so we will not be really offering extensions on the project. Now on to the grading details, the nitty-gritty. There are two big components in this class. It is the final exam and the project. The homework will nominally be worth 0% in the class, which means that the actual submissions are not going to be graded. We have only one GSI. So it's simply not feasible. We don't have the bandwidth. And in the era of LLMs, what we want to do is we want to really encourage you to focus on learning the material. I think Anand put it really well that, using an LLM to do your homework is the equivalent of, instead of going for a run around the block, you drive around the block. The point is the workout. The point is not the destination, okay? So doing the work is what is going to help you learn, not writing the answer in a box. And so the whole point is to encourage you to do the work. So we are not going to be really checking if you do the work. We will, in the event that there is a boundary case on your grade, you're extremely near some boundary, we may choose to go back and look at the homework and see if this is a case where we want to make some kind of exception. However, in general, the homework will not be looked at. So 60% of the class will be the final exam, 25% is the project, and 15% is participation, which we will talk about in a minute. Both the final exam and the project have a gating effect. What does that mean? It means that if you fail the final, you fail the class. You can't have an outstanding project but fail the final and pass the class. Similarly, if you fail the project, even if you have a perfect score on the final, you will fail the class. The key reason for doing this is to prevent free riding on the project. Because we do not want to have situations where we have groups of 4 students and only one of them or 2 of them are doing the work and the other people are not doing the work. So it is essential that you keep up with the class and do the work, because the way to do well on the project and be able to participate fully is to make sure that you know the material, doing the homeworks, doing doing the discussion sections. So this is all critical. There will be no curve in the class. You are not competing with each other. We have already published the bins to the website. These will be the bins that will be used for grading the exam.
The whole class.
The exam and the whole class, yes. Okay, so homework policies. There's a grade scope code. You might want to write this down. It's on the website too, even if you don't write it out. Please join grade scope. You have to submit homework 0 there, remember. There will be weekly homeworks. They will be due every Friday night. The grade scope deadline will be set to the end of the semester. So the last week of semester will be what the grade scope deadline will be set to. So you can technically submit the homework after, but the deadline is Friday night. Okay? Does that make sense? So that means that if you have a need for an extension, take the extension. But know that you're taking an extension, and know that that means that you are accepting the responsibilities that come with that extension. So we strongly recommend keeping up. I already talked about creating accountability through a study group. We already talked about the homework being 0%, and we may look at a random subset of your homework if you're close to a grade boundary. Finally, doing the homework is really the best way to learn the material. Historically, if you look at the exams, there have often been questions on the exams that are very, very similar to homework questions, or build on the concepts that have been talked about in the homework questions. Okay, let me pass to Anand.
Great. So let's just talk a little bit about the background we expect. So this is 2025. It's not 2015 or 2013 or sometime in the past. We understand a lot, and to give you the best deep learning class, we're going to try to use and get you to the edge of understanding that we have. So we expect a mastery of machine learning at the level of 189 or stat 154. We will not be reviewing, we'll set notation, but we're not going to reteach you basic machine learning. We're going to need it to build on. We expect a mastery of linear algebra and optimization at the level of EX127 to 27A. We are absolutely going to be needing, optimization is the workhorse for doing modern deep learning, so we're going to need you to know that. And have facility with doing the manipulations. We'll need probability at the level of 126, or data 140, or stat 134. Probability is the language we use to talk about things like generalization and a lot of intuition and principles behind which the algorithms and the approaches are designed come from probabilistic reasoning. If you don't have a deep familiarity with that, you won't understand it. So we require it. We're not going to teach you probability. What does this mean? It means that when you say we're not going to teach it, we're not going to teach it to you in lecture, and we're not going to support it in office hours. We're not supporting it in any way. So we can point you to stuff that you can read, but you have to know it. You saw the level of staffing we have. It's not feasible for us to teach you background material. Yeah, and to get if you just wanted to learn about deep learning in a cookbook manner, we strongly recommend you go and take advantage of the vast number of YouTube resources and other free resources out there that will give you lots and lots of recipes and stuff you can use to do deep learning. That's not this class. It's not the point of a Berkeley class. So we expect you here if you actually want to understand and learn the material, and to the best of our ability. Okay? So now you have a sense of the background we expect and we will be counting on. Let's talk about, we've seen about the homework. The homework will have written questions involving proofs and derivations and things like this. We expect you to do them by hand. The exam will be, remember, handwritten 3 hours in-person exam with nothing else except you and the exam. But the project is different. So a lot more details will be announced on ED, including all the logistics and sub-deadlines and things like that. But the key points are the project is a group project. Again, given the number of staffing, we cannot support a whole bunch of individual projects. We just don't have the resources. Groups of four. Groups of four can mix and match between undergrads and grad students. For the project itself, there will be a few options. Each of the options will be open-ended in that it will allow you to get however far you want to get close to the research frontier, and will build on, as well as build on published papers to allow you to demonstrate your understanding of deep learning. The project will require you to learn things on your own that will not have been covered in lecture, because that's the reality of the subject. However, for undergraduates taking the course, as well as graduate students from EECS, you will have to choose between the project options we give you that we'll support. There'll be room within them, but they'll be bounded. Graduate students from outside of EECS will be permitted to lead projects outside of our specified topics, based on aligning with their research and the like. We will publish more details about that on ED later, so you can understand what's in scope. On those teams led by a graduate student or 2 graduate students or 3 graduate students from another department, undergraduates are permitted to join those teams as well. The reality of deep learning is that you have to use computers. We are trying to secure some compute resources for you, and we have made some partial progress in this direction. However, the compute resources we are able to secure from wonderful national level programs are not sufficient to actually enable all of you to do the best projects that you might want to do. Let's just be clear about that. So you might need to bring your own compute for your projects to go beyond. We'll try to make sure the homeworks and all can run within Colab, free tier, and what you can do on your modern laptops. But even there might be the explorations you want to do yourself that go beyond. So we'll try to get you resources, but you might need more.
And in keeping with the Berkeley ethos, if you have resources that you can use, please use them so that the resource that we will obtain are available to those who do not have those other resources, right? So just be, we're doing our best to get as much as we can, but it's still finite, whatever we're going to get. So
yeah, for that,
and we'll have to share it.
For that, again, if you have any complaints about that, don't talk to us. Talk to the higher level people in the campus administration, the governor, and your senator and representative for understanding what it takes to compete in the modern world. So the project will involve lots of work on your part, of course, but you'll have to submit proposals. There'll be multiple levels. You'll have meetings with us. You'll have to submit drafts. There will also be an individual component to the project that's not group, which is you'll individually have to participate in peer review of other people's submissions and give detailed comments and feedback so that everyone can do the best projects by the end. It's also just a part of life in this area. So your actual grade on the project, the entire group will get 1 grade for the technical material that they have done, and that will be modulated by your individual performance as a peer reviewer to get your grade. So if you do a really bad job as a peer reviewer, for example, not doing your reviews, then you will get a 0 on the project, because the 0 will multiply even your spectacular other project. Okay? So you have to do all the work. Basic philosophy in this class is you have to do all the work. There's no escapes. So if you want to do that, be here. If you don't, there's 400 people approximately want to take the class, 100 seats, make room for somebody who does. The final component of the course is participation in citizenship. So what does that mean? It means that we expect you all, as a member of the community in this class, do your job in making the class better for everyone involved. Everyone starts off with 0 in participation, which is a failing grade. So what do you need to do to participate in this class? There are 2 components. One component is ordinary participation, the things that one expects people to do in classes. What does that mean? It means attend and actively participate in all the weekly discussions, which means every week, go to discussion and participate. The way that discussions are structured, if you are there and participating, the course staff will know that you are there and participating. There'll be small groups, you'll be working on problems, things like this. Some people, that may not work for you, or you might not be able to do it every week. We're aware of that. And so you can also be actively helpful in the online forum. Okay, this will also get you ordinary participation. So this is expected from you. Of course, if you don't want to do this, why are you taking the class? And on top of that, we are going to expect 4, at least, special contributions. We'll put more details about this in the Ed forum. But these are things that you can do that involve a little bit more work, that make the class better for everyone, that also actively engage your learning in a more detailed way. So one option is going to be take one of the modern LLMs. We'll have a sign-up way for you to sign up, so you don't have lots of overlapping things. So for example, go to Gemini and say, OK, Gemini, I'm going to use Gemini to solve the homework. And we'll record a trace. We'll put details about this. Record a trace of you interacting with Gemini as watching how Gemini solves the homework problems. OK? We'll expect you to then annotate that trace with your own comments, critique it. Sometimes Gemini will one-shot the problem, for example, but sometimes it won't. So engage. See what's going on, and give us a report on what happens. You must do this at most once. So you can't do all 4 of this. There are going to be 3 other choices, one of which is, so I didn't finish making the slide. One will be to do the same thing for code. So we'll have homework assignments that involve code. So then C, using copilots, Cursor, windsurf, any of these different tools that you have, or just the straight LLMs directly, and see how do they do on that coding problem, and interact with them as well. Why do we do this? We expect students in a course like this to walk away not just with an understanding of deep learning from a theoretical and a, let's say, 2019 level way of engaging with a computer, but also the modern way. So we want everyone to have at least some practice doing this, okay? No, it's not worth it. So this is the second thing. Third thing is also related to code. It's to the code. So we built these homeworks over many semesters, and they were built trying to get them out the door so they can teach the right thing for students. They're not the best written code. They're not actually code that we would be proud to have as our demonstrations of code. Another thing you can do as a special contribution is to consult, critique, look at online descriptions of what is good coding style, both Pythonic coding style or also specifically machine learning oriented, and take one of the problems and clean it up, okay, to reflect that style. This is good for you, and it's good for everyone else, okay? These are 3 examples of special contributions. There's one more, very important one, that I cannot explain to you in a way that you will understand yet. However, it has to do with the following. The field is moving and keeps moving. Some of the homework was built, oh my goodness, as far back as 2022. And so there have been advances. We do not have the staff bandwidth to actually take all of the problems and make them aligned to our current best understanding. There will be another option for you to do that, to add parts to problems that reflect things we're going to teach you that were not understood in 2022, okay, as an example. We expect everyone to do this because this is how you will really learn and master the material. And you'll help everyone else as well. Okay, so I will pause here now for questions because we're going to then switch into talking about deep learning. We talked about a bunch of administrative stuff. Remember, the short version is go to the website, read, go to Ed, and find out. But if anyone have any questions, this is the time we can take any questions right now. Yes?
Regarding homework, actually special contributions. So to get full credit, we need to do at least 4 of them, but detailed LLM has to be used, can be used on only once.
They do 3 from the others as well. And the others also have caps.
3 other can be just mixed and match.
Yes, mix and match. I mean, you can't just do the coding one also. We'll cap that one. But you don't have to do all of them. But we encourage everyone to do one of each.
It's good for you to try one of each. That's why it's 4 categories and 4 things, so you can try them. But if you really like doing one kind of thing, we're not going to make it super strict. We'll write up guidelines. I mean, the objective of this is not to nickel and dime. It's to try and make the incentives for you to do work aligned with the incentives for your learning, right? So that's really, so why do we say that detailed LLM reports are only allowed once? Because, let's admit, it's easier to copy-paste a problem into Gemini and see what it turns out. And yes, there's some value for your learning, but writing code has a different value for your learning. And so if you diversify the things you do, you will learn more. That's basically where this is coming from.
Notice that basically the way these are structured, you cannot cheat, except by outsourcing to another person, right? Yeah.
How are you guys planning to count the contribution?
Great question. So at the end of the semester, we will give you a self-grade form that you will use to document, have a picture of yourself so we can match you against people's memories of who was in a section, as well as document what are your key contributions with posts, and then we can just check. Yeah, we're not going to go through it. Remember, there are a few of us, but we are structuring things in such a way that the incentives on you are just to do the right thing and learn the material.
For non-EECS graduate students that are in the wait list, how is the wait list going to be topped? Is it going to be just based on, are certain people given preference in the graduate wait list, or is it just...
We actually don't even have control over it. The instructors don't have control over it. The department auto-processes it, so...
Yeah, basically we don't know.
The number of emails that I have saying, I have emails from colleagues saying, can you please help so and so get in the class, and we just don't have the control.
But you have to do homework 0.
Yes.
If you don't do homework 0,
We have a negative.
we'll block you from getting in the class.
Yes.
I'm a current enrollment student, and I wonder if there's going to be room for that.
We don't know.
Yeah, basically we don't know. That's the key answer to most enrollment questions. But you better do homework 0. if you don't do homework 0, you're not getting in.
Yes.
Grade scope.
Grade scope. The code is on the slides. It's on the website. Enroll yourself on grade scope.
We will not be using B courses. So,
Yes.
yeah.
Sorry, I have one more question. I don't know if you guys got to this, but how is the material from this semester just going to be like same as you said 2022?
No. That's the point.
Oh.
That's the whole point. So we are doing our very best to read papers that have been published in the last
Month?
year and get the material updated. Of course, there's going to be some material that is canonical, historical material. Like the definition of a RELU is still the same in 2022 and 2025, right? The SVD, even more fundamental, also is required for this class. We won't be teaching it, but so there's stuff that's fundamental, and that's going to be the same. But there's stuff that's new, and what we're trying to do is, trying to digest this material that's not even in the textbooks yet and present it to you.
So for example, right, some of the things that make us tip into this vast literature, that make us tip what is relevant to teach you, is a kind of sense of stability. Like, is this understanding that's actually having impact? And so recently, the release of certain Chinese open source models, right? I think Kimi 2, right? In particular, made it very clear that there were things, as well as Llama 4, that made it very clear that things that we were kind of maybe sitting back on, that is this really something that everyone needs to know? Or, is it still, too far on the frontier to, you guys need to know it, okay? So that kind of stuff is going to be worked into the class. So the material in the class is different. The LLMs, without reading papers, cannot do well in everything in this class because there'll be information beyond their training cutoff date. Okay? So, yeah, the material in the class will keep evolving and changing. Just to give you a sense of this, when I first taught the class in fall 2022, just before the beginning of the class, Stable Diffusion had come out. Just before. By the end of the class, there was the release of ChatGPT. During the majority of the class, ChatGPT did not exist. Okay? And like this, there have been advances sort of in the different terms, and we try to, kind of make adjustments as we can to make sure you are at the right place. Our goal isn't just that you understand what is understood now, but that you are in the right position to be able to understand the new stuff that will come out later this year, next year, the year after, and ideally 4 or 5 years after that. Okay?
Yeah.
Is homework 0 released on the grade scope? I just checked, and it says the outline for this assignment.
So I'll explain this. So Gradescope is the place where you will submit your homework. Your handwritten homework will be scanned in, concatenated with the PDF of your code, your notebook, together into one PDF, and you will upload it. We will not put outlines up there. You're just going to submit there. Think of it as a place to place a file. That's what we're going to do. We don't have time to build outlines, okay? The homework is on the website. So if you go to ex182.org, you can click, and there'll be homework 0. You can see it, okay? Don't recommend doing it now, but you will have to go through and do it we have an extended time period, not 1 week. We have until Friday of next week for you to do it.
Yeah.
So I have a last question. So for the final project, like when will we know like the scope and think about our ideas for?
So the final project will be due at the end of the semester, and we will expect that you will need to use a bunch of the techniques that you are learning in the class to do the project. So we're not in a position to announce the final projects yet because you don't have the material to even, be able to conceptualize what it is. So we're expecting to release the final project somewhere around mid-semester, mid to late semester, and then you will have the second half of the semester roughly to work on them.
Yeah, we'll have lots of detailed sub-deadlines and so on. But right now, it would just be gobbledygook.
Yes?
If the lecture, slides or recording be uploaded, or if...
The lectures will be recorded. Yeah, the lectures will be recorded and then posted after the lecture is done.
However, we strongly recommend that students take handwritten notes for everything. Okay, whether you watch a video lecture or you're sitting here. Not for administrative stuff, but when we start talking about material, take notes. Okay, this is not a sit back and casually watch kind of class. It's not a double speed watch lecture and checks their phone while talking to ChatGPT. This is just not that class. If that's what you want, don't take the class. Full engagement is what we ask for. Okay,
yes,
and last questions. Yeah.
Would there be any sleep days for homework zero,
There's absolutely no slip days for homework zero. And like I said, you can submit your homework to Gradescope later. The point of homework is for your learning. But homework zero is a hard cutoff, and you have more than a week's notice to finish the homework.
And everything in homework zero, you already know how to do if you know the prerequisite material. Nothing we're going to talk about today or other days is going to be required to do homework zero. You can do it now.
Okay.
So
great.
Let's move on. Okay. Yes. Okay. So now we have to confront something about deep learning itself as a subject, which is deep learning is a subject where our understanding of it is way, 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 way better than it was in 2015, in the sense that a 1-year-old is way more capable than a newborn, okay? But we are still babies overall as a species in terms of actually understanding this material. So this is what we expect your experience and our experience many times to be like in the class. That's a feeling you'll be familiar with.
Bye-bye, Bob. Bye-bye. Bye-bye.
Okay. So we'll do our best to teach you what's going on, but there's lots of times where you will experience a lot of internal feeling of I'm not sure I'm comfortable with what's happening here in terms of understanding. Because there's a style in which you have learned your foundations, your mathematics, your probability, your principles of how we think about algorithms and code and linear algebra and optimization and physics, which is very, very stable and well understood and systematic. There is a rigor. And a connection between the rigorous understanding and experiments and the gaps between what people understand and what you are taught. I mean, some of them are being masked, but some of them are more subtle. In deep learning, it's much more in your face that we don't understand things. So we will keep pointing this out as we go in the class at different places, but you just have to acknowledge it. So let me see what I have. Okay, here. So when we talk about deep learning, like, what are we actually talking about here? What is this class about? So fundamentally, deep learning is a class about neural nets. So what is a neural net? A neural net is fundamentally a simulated, typically, analog circuit. So first thing is, this is not the values we're interested in are continuous values that we're working with. We will represent them with floating point, but they're continuous values. And these circuits are largely parallel in what they do, and they're doing information processing. But to set the very, very many parameters associated with this circuit, we have to use an optimization algorithm to set these parameters. We don't handcraft them. At times in the homework, we will ask you to handcraft parameters to help you understand the relationship between the parameters and trying to achieve a certain objective. But in practice, we're using an optimization algorithm driven by data. And so that's what this class is about. What makes it deep learning, why we call it deep learning, is that the circuits that we're talking about in practice are deep and they have many, many layers, many circuit elements they have to pass through before you get to the end. Okay? That's what we mean. So we do this with a goal. We would have, like the learn circuit, the result of the optimization, driven by data, to approximately capture relevant patterns underlying the data. This is what it shares with machine learning. It's a subcategory of machine learning, where those patterns are present in the data that's used to train it. And we want to do this so we can use the resulting circuit to solve problems involving new data. Okay? What problems? Problems for which whatever patterns we've learned are relevant. Okay? So that's this kind of connection to regular machine learning. So this sounds great. Okay, fine, you want to do this. But the reality of the subject is we barely know how to do this. We build things, we try them out, they work. We have reason and intuitions for building it, but these don't often match the level of rigor you might expect, for example, if you were constructing a bridge. So how to wrap your head around it? In this class, we'll basically have two approaches we will help you wrap your head around it. The first is a joke. Okay, so I will tell you this joke. This joke will be told over and over again in this class to help explain why things happen the way they do. The joke goes like this. You might have heard this joke. So a person is walking, and it's a night, and they see a drunk man kind of searching on the ground, near a street lamp. So they walk up to this drunk man, and they say, "Hey, what are you doing? What's wrong?" He goes, "Well, I lost my keys, and I'm looking for them." And so the person asks a follow-up question. "Did you lose your keys right here?" And the person says, "No, I lost my keys over there." And the person asks, "Why are you looking over here?" He goes, "Because here's where the light is." Okay? So this joke is actually the essence of what we do in deep learning throughout. Many times, you'll have a very natural question, which will be, well, you said we wanted to do X. Why are we doing Y? And the answer will be, because we understand how to think about Y. We do not understand how to think about X. So we're going to do Y. Okay? Now, the pragmatic sense of this is actually very reflective of what's in engineering generally, which is it's better to do something that has some chance of succeeding than to do nothing, which has a 100% chance of not succeeding. Okay? Now, ordinarily in your classes, this is not, although it's a very fundamental principle, it's not in the foreground. In this class, it will often be at the foreground. So, what are the things that we understand? This XKCD is a very relevant one. So you take a chance to look at it. Many of you might have seen this already. So in case people in the back can't read it, There's a stick figure person standing on a big mess, having matrices and lambdas and stuff in it. And the person there says, "This is your machine learning system?" He goes, "Yep. You pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right." Okay, so you will find in this class that we will lean often on linear algebra. So it's good to acknowledge the many reasons why. One reason is linear algebra is something that we understand. And it's something that we have intuition about, that we can connect to geometry. So if you're thinking about something, it's easier to think about things in the context of something you understand. Second, linear algebra is something that we have made computers very good at doing. They match naturally to parallel processing that happens on SIMD processors and other GPU-like machines. And so if you want to do something, you might as well do it using something you know how to do fast on a computer. So we use this as a building block. But don't forget it's what we understand. So many times we'll be building you intuition using simple linear algebraic formulations. And you'll say, how do I know this applies to my deep learning problem? And the answer is, well, we understand it here. And it seems to have intuitions that carry over. And so we will use it. Okay?
And if I may add a comment. Is my mic on? Yes, OK. So I just want to admit that when I started learning deep learning, this was one of the things that made me most uncomfortable about it. Like, I'm used to doing things where I can prove a theorem. And I know for 100% that I have optimized the parameters. I know exactly that I'm doing always the perfectly right thing. And for someone who is trained to do that and has come through taking classes where you're always used to doing that, this look at it this way perspective it's a perspective shift, but one that I've found is very useful and very mind expanding in really nice ways. It's interesting to see how your minds have gotten trained into having a particular way of doing things, and having this new perspective is actually really valuable. On the flip side, what I also see often is that there's a lot of, because kind of no one understands anything anywhere here, there's a lot of what people call, or what I call, ML broism, where you just shoot off a bunch of then you take the some big term and then some other jargon and then some other jargon, and you don't really understand what it means, but you hope that the other person also doesn't understand what it means. And you just talk in these big words, and that is also not an ideal situation, and that is not where we want you to be. What we want to develop is a sense of groundedness in fundamentals that comes from the training that you have developed through taking hard classes like 126, like 127, where you've ground out these large proofs. And so you have that aesthetic and elegance of mathematical beauty, and bring that to the linear algebra soup, right? So that we can try to see the elegance and the beauty in that soup. So these are two different ways of thinking, but they're both really important, is what I wanted to add.
Yeah. And again, another joke. So there's an engineer, a mathematician, and a physicist are all drunk, and they have decided that all the odd numbers are prime. And so they proceed to talk about it. And the mathematician says, well, 3 is prime, 5 is prime, 7 is prime. It follows by induction. They're all prime. And the physicist says, 3 is prime, 5 is prime, 7 is prime, 9 is experimental error, 11 is prime, they're all prime. And the engineer says, 3 is prime, 5 is prime, 7 is prime, 9 is prime, 11 is prime, 8 is prime. Okay, so this joke, you will often feel, so what we're hoping is that you will maintain a little bit of your sense of groundedness to know when we are pushing things beyond, and to feel a little bit like sometimes the physicist in that joke who says, okay, this isn't quite right? But okay, it isn't quite. But at times, for practicing in deep learning, you will have to take that engineer's point of view and says, yeah, I know this is not right. This doesn't follow the theorem, but I'll do it anyway. Okay? But again, this is part of the aesthetic. You just have to learn how to do this. So now, I want to talk about what this feels like, to maybe ground people a little bit more in your education has come at a very special time for human civilization in that we actually understand a lot of stuff. But understand that for a very, 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 very long time, all of the sciences grew up as alchemy, where people were trying to turn different metals into gold, develop potions of immortality, cure various diseases, forecast when appropriate heir would be born, and so on, and do various tasks that would allow them to get money from people who have lots of money and power, so they could go on and continue to fiddle with various chemicals and put stuff together. Okay? I mean, to an extent, if you watch what's happening in the venture world and so on, this has not changed. But the important thing is, all of that progress that happened by alchemists gave us modern science and chemistry. They built the experimental equipment. They figured out how to do all this stuff. And remember, human beings have had amazing ceramics for thousands of years before they understood even the most basic thing about how ceramics actually work. People built cathedrals before they understood F equals ma. Okay? So the fact that we don't understand many things in deep learning, you can think about as a little glimpse that you get to experience today of connecting to the worlds that your ancestors lived in forever. They worked hard, they made progress, they made amazing things, despite not understanding them at the time. And then understanding sometimes came 10 years, 100 years, 1,000 years, 10,000 years later. So we don't know where we are in this process. So it's okay. Okay? You'll have to remind yourself of this. This is okay. So now, I want to talk a little bit about some of the history. We're not going to be taking a largely historical perspective. Occasionally we'll mention history. But neural nets are actually something that has been around for a while. And neural nets have gone through various phases of excitement. And so back in the 60s, 50s actually, between the 50s and 60s, you had the idea of the perceptron. You had the idea of doing pattern recognition using these things, having data-driven methods of LMS, which is basically gradient descent. Then you had, in 1969, this book which described the fundamental limitations of one-layer neural net. And that resulted in, among other things, in a crash, right? And so neural nets were like super exciting and hot, and then went through a period of, oh, they're totally useless and they can't work. Historically, this has also been connected to when you outstrip the available compute. Okay, the actual compute you can do, the things you have to work with are no longer capable to go any further, and there's a crash of disappointment. So it's like a neural net winter that happens. So the first golden age of neural nets ended. Then, in the 80s, compute got better. Other advances happened, fuzzy logic, other things were brought up. Backpropagation was moved from control theory, where it was developed, into training neural nets. And you had the second golden age of neural nets that basically ended at the end of the 80s, the beginning of the 90s. Okay, again, a crash from the neural net point of view. Although people kept working. Smaller groups of people kept working in the area. And people realized they could do a lot of this stuff much better using stuff that had math that we understood better. So we had a second golden age of neural nets that, again, went away for some time. Then you had the 2000s. What happened next is parallel developments, right? You had computer graphics, you had video games, which led to GPUs. So GPU's main market was video games. And so lots of people wanted to play video games. So GPUs got better and better and better. And then in the 2010, 2009, 8 timeframe, people realized, oh, you can use GPUs to train neural nets. And they're faster. You can make bigger nets. And then in 2012 begins the modern, current, the phase we live in today, golden age of neural nets, where suddenly the paper, AlexNet, beat all previous methods for doing image classification, and made it that neural nets before that point were viewed as an interesting niche tool. So they were really good at doing things like handwritten digit recognition, other little tasks. They were bigger in Japan, where they were used in many consumer things as a small thing. But at this point, they were like, wait a minute, let's just revisit this. And from there, you had the building forward of the wave that we live in today, right? Which is this new golden age for neural nets. So it's good to acknowledge this history a little bit. We could keep going and talk about the different developments for this in this age, and we will do that in the course at different points when we introduce certain key building blocks. But I wanted to give you the kind of prehistory back. Now, our perspective that we'll use in this class is all going to be post-2012. Okay? We're not going to talk that much about details of things that were understood back then. Fortunately, you've taken a machine learning class, you've already seen backprop, you know how it works, we don't have to review that. So we'll largely focus on stuff afterwards. Okay, so any questions on this history? And then I'll switch to the board and start introducing some material for the, for the course now. Any questions on prehistory or other issues? Okay, great. So let's switch to the board. So let's just think about something. Now, I expect most people, everyone, has seen a multi-layer perceptron before in your previous machine learning class. What I'm going to try to do here is to approach the question from a different point of view to connect some ideas. So we're going to use a neural net to approximate functions. So how do we think about this? The easiest way to start thinking about it is to think about approximating a function, f, that goes from the reals to the reals, a univariate function. Okay? So the input is x, which is a scalar, and the output is y, which is also a scalar. And so in discussion next week, we'll also engage with what I'm talking about right now. So how do we think about functions from scalars to scalars? Well, you've been doing this for a long time, right? You can just plot them. X, y. And so when we talk about function approximation, we would like to think about approximating an actual underlying function. And now, in the context of machine learning and neural nets, we want to approximate a function, and we want to learn that approximation using data, samples. So we can visualize all that. So we have some function. So here's the function, our desired function. And we would like to have a neural net, so we have a neural net. N. And N is going to be defined by some parameters. Theta, these are parameters. And the neural net matches input-output what you want. So N is going to take a single scalar input and will output a real. Okay, so we have a neural net that takes a scalar input, outputs a real, defined by some parameters, such that we can approximate functions. Everyone with me? Great. So now we think about how do you want to approximate a function? So you probably first saw approximating functions with other things back when you learned calculus, when you learned things like Riemann integration. Right? So when you learned Riemann integration, what you did was you took a function and you approximated it by a piecewise constant function. And you said, hey, if I take this function, let me use another color. Lots of different ways to do it. You get the idea. Right? So this is a piecewise linear approximation. So not piecewise linear, piecewise constant. Piecewise constant. So when we think about neural nets, we have to think about how we do the approximation, and our goal in doing the approximation is manifold. We would like to do the approximation in a way that has good approximation properties. We'd like to be able to approximate the function well. We would also like to be able to do the computations involved in doing the approximation efficiently, using linear algebraic tools, together with other tools. And we would also like it to be possible to train this neural net to follow approaches like gradient descent to actually move the parameters. Okay? So piecewise constant is one approximation, but we can also have a different approximation, right? We can do piecewise linear. So a piecewise linear approximation would look like this. This is piecewise linear. So again, you saw piecewise linear approximations, probably when you, also in your calculus class, where you learned something like trapezoid rule for integration. Right? These might be bringing back memories for what you learned a long time ago. And so you can see, at first glance, you can see, okay, piecewise linear is a better approximation than piecewise constant. What does that mean? It means that for the same number of kinks, it is closer to the function, right, in places between the kinks. So that's one aspect of thinking about approximation, is approximation quality, how good of an approximation it is. But the other thing you care about from the neural net perspective is how do you represent it? Is it possible to represent piecewise linear approximation using parameters that are friendly for optimization and for computation? Okay? So the question becomes, how to represent / parameterize a piecewise linear approximation. So what do we need to know? So when we think about parameterization, it's like I need to describe this piecewise linear approximation using a set of numbers, such that given the set of numbers, I know how to evaluate the function. Everyone with me? Okay, great. So you could immediately see that in these cases, there's lots of choices to how to do this. Right? There's lots of different choices by which you can think about this piecewise linear approximation. So the first thing you need to look at in this, so let me zoom in on this piecewise linear approximation thing a little bit. Zoom in, because I want to talk about it. So I'll just zoom in to some piece of it, to some little section, okay? So if I think about a piecewise linear approximation, look at this part. What information qualitatively do I need to convey about this purple thing so that you can know it exactly? What do I need to know? Yeah?
Step size.
So I need to know what do you mean by step size? Okay, so I need to know the lengths, right? So I need to know also, one way of thinking about it is I need to know where these kinks are. Right? What's the spacing between them? So is this?
Yeah, I don't know what I can.
So locations of these kinks. Okay, what else do I need to know? So now I know where on the x-axis, so these locations are here, 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 and here. Okay? What else do I need to know? Yeah?
Slope.
I need the slopes. Okay, so slopes. Okay, good. I need to know where the kinks are. I need to know where the slopes are. What more do I need to know? Is that enough? I need to know how high this thing is. Okay? So now, this is the first place where you should start feeling, okay, wait. How much do I need to know? Okay? If I told you the location of the kinks, and I told you all the slopes, and I told you it was a piecewise linear approximation, meaning it's a continuous function, how many y's do I need to know which function it is? 1. I need to know the height somewhere, right? Okay, so you can kind of see there's some kind of information I need to know to understand this piecewise linear function. Okay, now comes the next question. How can I represent this information in a different way, in a way that's convenient for me to apply parallel matrix type of computations to do the computation? Okay? So I can just describe this information theoretically. If I tell you all this information, you can replicate this. But that might not be the most efficient way to do it. So one of the useful ways to think about it is, so now we need to think about implementation a little bit. So we know the kinds of operations that we know we like to make computers do is things like multiply, adds, right? Multiplies, adds, stuff like this. So we would like to implement this kind of function, so let's call it neural net theta of x, in ways that involve multiplication and addition. So one way to think about it is to think about it as some kind of a sum over little pieces, little things. So I want to sum with weights of some kind. Well, maybe I won't use this. I'll use W. And I'm going to sum up some other functions. G theta tilde I.
Maybe write a little bigger,
Yeah, I should write a little bigger.
or even on Discord.
So I think I'd like to be able to represent a piecewise linear function as a sum, a weighted sum. Now, why do I like this? Because I know, in principle, that this kind of sum type representation is going to have natural parallelism that I can exploit. Because I could presumably compute all of these things in parallel, multiply them in parallel with their individual weights, and then add them up. Okay, so this is like friendly for computers. So you think, okay, if I wanted to have this kind of information, so all this information that I needed, this height, these slopes, these locations, all have to be somehow embedded in the learnable parameters, like these weights and whatever these theta tildes are. Okay? So it turns out that there's a way of thinking about this that's natural. And the natural thing is to think about what this little function in here should be like. So you think, hey, wouldn't it be nice if I could, instead of thinking about a function that has arbitrarily positionable kinks and slopes and so on, as instead being something that's defined this way. Okay? Where I have an arbitrarily positionable kink, elbow, and a slope. So if you think about it, if I add together a bunch of functions that are all sort of flat and have some slope that I can modulate, then I could certainly start at 0, go up, and then change my slope later by adding a different function that moves the slope down. You see how I could construct things this way? Okay, so this is nice. This gives us a way to do that. Now, the great thing is that these kind of functions can be put together out of even simpler things. So this kind of function, what is this? This kind of function is a max of 0 and some wx plus b. This is a straight line somewhere, so it's defined by wx plus b. This is a max in this. So this kind of operation, max 0 something, is what the ReLU is. Rectified linear unit. And next time, you'll see how to connect this kind of thing to more linear algebra and set everything up so you can see the approximation of this. Okay, because we're out of time. We have office hours in 400 Corey. There's another class immediately after us, so we can't really answer too many questions here. There'll be a couple, 1 minute, but then we have to move out.